We just got a massive wake-up call about Mars. A paper released just days ago, on November 10th, confirms that water didn't just vanish from the surface of Gale Crater, it retreated underground. The data shows that groundwater was active and interacting with the subsurface long after the surface became a frozen wasteland. But knowing the water went underground is only half the battle. Knowing if life could survive, there is the other half. And that brings us to a crucial realization. When you combine this new discovery with the data we've ignored for the last year, the picture becomes clear. We have been looking for Martian life in the wrong place for 50 years. That's not an exaggeration. That's what the data actually shows. Since the 1970s, every rover, every lander, every billion-dollar mission we've sent to Mars has been rolling across the surface, drilling into rocks, scooping up soil, and the whole time, the actual evidence of ancient life, if it exists, has probably been hiding just meters below our wheels. Protected, preserved, waiting. The Martian surface isn't just barren, it's actively hostile to the very thing we're searching for. The planet lost its magnetic field about 4 billion years ago. Without that shield, solar radiation and cosmic rays have been bombarding the ground ever since. Any complex organic molecule sitting on the surface gets shredded over geological time. The bonds between carbon atoms, the backbone of all life as we know it, just get broken apart. Add in the perchlorates in Martian soil, these oxidizing salts that become even more destructive under ultraviolet light, and you've got a planet that essentially sterilizes its own surface. 99.9% of complex organics would be destroyed within 300 million years of surface exposure. And Mars has been like this for billions of years. So even if life flourished there when the planet had rivers and lakes and a thicker atmosphere, any trace it left on the surface is probably gone by now. Degraded, oxidized, erased. We've been reading a book where someone burned most of the pages. But here's what changes everything. An international research team led by scientists from Portugal, Spain, and the University of South Florida went into volcanic caves on Lanzarote in the Canary Islands. These caves are lava tubes, tunnels formed when flowing lava crusted over on top while still flowing underneath. When the eruption stopped, the molten river drained out, leaving these massive hollow passages. Lanzarote is one of the best Mars analogs we have on Earth. Similar basaltic rock, arid climate, and it turns out similar mineral deposits. The team collected samples from 6 different lava tubes. Some of these caves formed just 300 years ago. Others date back to the late Pleistocene, millions of years old. They use the exact same analytical techniques that are currently on the Curiosity rover, and that will be on the European Space Agency's Rosalind Franklin rover when it finally launches. Pyrolysis, gas chromatography, mass spectrometry. The same instruments, the same methods. And what they found was remarkable. Inside these caves, they discovered that certain minerals, specifically sulfates like gypsum, act as chemical time capsules. When water-carrying organic matter seeps into a cave and evaporates, it leaves behind these sulfate deposits. And as the crystals form, they trap whatever's in that water. Microbial cells, DNA fragments, lipid molecules, the fatty acids that are the building blocks of cell membranes. All of it gets sealed inside the mineral structure. The researchers recovered preserved DNA from bacteria. They found lipid biomarkers with carbon chain lengths that only come from biological sources. They detected isotopic fingerprints that distinguish biological carbon from volcanic carbon. And here's the critical part. These biosignatures survived because the cave environment protected them. No ultraviolet radiation, minimal cosmic rays, stable temperatures. The volcanic rock overhead acts like a vault door, sealing everything inside away from the destructive forces that would obliterate the same molecules on the surface. Professor Bogdan Onak, one of the lead researchers, put it plainly. This study highlights lava tubes as potential refugees for microbial life, holding significant implications for astrobiology, particularly in identifying biosignatures on Mars. Now Mars has lava tubes, a lot of them. Over 1,000 candidate cave entrances have been identified from orbit. Most of them are in the massive volcanic regions around Tharsis and Elysium. And these aren't small caves. Here's something that might actually stick with you. Martian lava tubes are roughly 100 times wider than Earth's. On our planet, lava tubes typically measure 10 to 30 meters across. On Mars, 250 to 400 meters wide. You could fit entire city blocks inside a single tunnel. Some estimates suggest volumes large enough to contain skyscrapers. Why so big? Mars has only 38% of Earth's gravity. That lower gravitational pull allows cave roofs to remain stable with far greater spans. The roofs themselves are estimated to be tens of meters thick. That's not just shielding, that's fortress-level protection. The first Mars cave skylights were discovered in 2007 by a researcher named Glenn Cushing using the Mars Odyssey orbiter. He found 7 caves on the flanks of Arcia Mons and gave them women's names: Dina, Chloe, Wendy, Annie, Abby, Nikki, Jean. And in 2010, a group of 7th graders at Evergreen Middle School in California discovered a previously unknown cave skylight on Pavonis Mons while participating in a citizen science project. It measured 190 meters by 160 meters with a depth of at least 115 meters. 7th graders, using publicly available satellite images. The entrances are there. We know where they are. What we haven't done is go inside. Let me paint you a picture of what preservation might look like down there. On the surface, radiation is about 0.67 millisieverts per day. At just 1.5 meters underground, that drops by a factor of 13. Go deeper under tens of meters of basalt roof, and you're approaching radiation levels comparable to Earth's benign subsurface. Any gypsum deposits that formed in Martian caves when the planet was wetter could theoretically preserve molecular evidence for millions of years. Maybe longer. The sulfate crystals don't just block radiation. They physically encase whatever was in the water when they formed. It's like amber trapping an insect, except at the molecular level. If life existed on Mars 3 to 4 billion years ago, when there was liquid water on the surface, and if that life retreated underground as the climate collapsed, we might be looking at a preservation window that spans most of the planet's history. But let's be honest about the limitations here. First, this study proves preservation is possible. It doesn't prove anything actually exists on Mars. No matter how perfect the caves are for keeping biosignatures intact, if Mars never had life to begin with, those caves will be empty of biological evidence. We might find fascinating geology, interesting chemistry, but no smoking gun. We have to be prepared for that. Second, the Lanzarote caves are wet compared to Mars. On Earth, organic matter enters caves through water percolation, through infiltration from the surface, through active biological processes happening right now. Mars is extremely dry and has been for billions of years. How would organics have gotten into Martian caves? Maybe through thin brines during warmer periods, maybe through vapor deposition, but it would have been a less efficient process. Even if life was there, the concentration of biosignatures might be much lower than what we see on Earth. Third, the researchers acknowledge that distinguishing ancient organic matter from recent contamination is difficult. The fatty acids they found, palmitic and stearic acid, are widespread across plants, animals, and microorganisms. They're not unique identifiers, and high-temperature analytical methods can introduce chemical artifacts that confuse the picture. This is 11 samples from 6 caves, a small data set. The conclusions are promising, not proven, and then there's the contamination problem. The team used sterile tools to collect their samples specifically because contamination is so easy in cave environments. Now imagine sending a robot, or eventually humans, into a Martian cave. How do we ensure we're detecting actual Martian biosignatures and not hitchhikers from Earth? How do we know we're not introducing our own microbes into a pristine environment that might still harbor native life? One researcher studying similar questions asked the obvious. How do we ensure that life detection missions are going to detect true Mars life rather than our life? That's not a solved problem, and getting into a Martian cave is an engineering nightmare. Current rovers are designed for relatively flat terrain. A cave skylight presents a vertical drop of 50 to 100 meters, followed by a floor covered in massive boulders. A wheeled rover would be trapped instantly. There are concepts being developed. ReachBot from Stanford uses extendable booms with microspine grippers to climb vertical surfaces like a spider. The European Space Agency's Daedalus is a spherical robot designed to be lowered into pits on a tether. JPL has the Axel concept, a two-wheeled rover that can rappel down cliff faces. But none of these have been tested on Mars. Communication is a problem because radio waves don't penetrate rock. Once a robot enters a lava tube, it's cut off unless it deploys a relay network as it goes, dropping communication nodes like breadcrumbs. No dedicated Mars cave entry mission is currently funded. The closest thing we have coming is ESA's Rosalind Franklin rover, launching in 2028, which will carry a 2-meter drill. That's the first rover that can actually access subsurface material protected from radiation. But it's still surface drilling, not cave exploration. So we're left with a genuinely frustrating situation. The science now says the best place to look for evidence of ancient Martian life is underground. The minerals that could preserve that evidence exist. The caves that could contain those minerals exist. We know where the entrances are. We have instruments that could detect the right signatures. And we can't get there yet. The 2019 Mars Extant Life Conference concluded that there is a realistic possibility that Mars hosts indigenous microbial life and identified 4 potential refugia: caves, deep subsurface, ices, and salts. The subsurface, extending from a few meters to several kilometers deep, is considered the planet's most stable, long-lived potential habitat. We're not just talking about finding fossils. Some researchers think living microorganisms could still exist down there. Gypsum contains water within its crystalline structure. Geothermal heat could maintain liquid water in deep caves. Chemosynthetic bacteria, like the ones that thrive in Earth's deep mines and underwater vents, don't need sunlight. They need chemical energy from rock-water interactions. That could exist on Mars right now. In South Africa's gold mines, researchers have found bacteria living 3 kilometers underground, completely isolated from the surface for millions of years. They survive on hydrogen produced when radiation from uranium decay splits water molecules. No sun required. Just chemistry. If Mars ever developed life, and if that life adapted to the subsurface as the surface became hostile, there's no physical reason it couldn't still be there, dormant in crystal cocoons or actively metabolizing in deep aquifers. We won't know until we look. The researchers in Mexico's Naka crystal caves claim to revive bacteria that had been trapped inside gypsum crystals for tens of thousands of years. If confirmed, that means cave minerals can preserve not just dead biosignatures, but potentially viable life in a state of suspended animation. Think about that. We might not just be looking for molecular fossils. We might be looking at something that could wake up. This brings us back to why this new research matters so much. For 50 years, the search for life on Mars has been surface-centric. Follow the water to ancient lake beds and river deltas. Look for organics in exposed rocks. The logic made sense at the time. But the surface is a decoy. It shows us the weathered, degraded, irradiated remnants of whatever was once there. The real record, if it exists, is underground. In the dark, in the cold, sealed in sulfate crystals that formed when Mars was young. We've been searching the burned library. The fireproof basement has been there the whole time. The question isn't whether Mars caves exist. They do. The question isn't whether they could preserve biosignatures. This new research shows they can. The question is whether we're going to go look. And right now the answer is not for at least another decade, maybe longer. Meanwhile, 1,000 cave entrances sit there, openings into a world we've never seen, possibly holding the answer to one of the oldest questions humans have ever asked. Are we alone? The evidence might be waiting in the dark. For more of the latest discoveries that reshape how we see our place in the universe, there's always something new, and sometimes the biggest answers come from the places we forgot to look.